we have a double integral from over the domain D. Sometimes they use R, sometimes they use D. And they describe D as a region in 2 dimensions as x values going from 0 to 4 and y values going from 0 to square root of x. And so it would be good practice, I think, for you to be able to look at the domain and try to draw the domain. And the challenge here is that you have to know a bunch of different types of functions. So you have to know how the square root of function, square root of x looks like without having to, plot points or take out your calculator just to be able to do things quickly. And, we studied the conic sections, for example, so a lot of shapes from those types of functions might be coming back. And so the absolute value, the square root, the exponential functions, these are just 2-dimensional functions that should, happen quickly for you. And when I draw this, I would like to draw the functions first. And I know that think of 0 as just a number, but it's a horizontal line function. But I'd like to draw the functions first. So I have 2 functions, y is equal to 0 and y is equal to square root of x, that I would draw. So my 2 functions are 0 and square root of x, sideways parabola. And then from here, I'm going to have 0 to 4 in my x values. So 0 to 4. And that's going to be the region that I have. If we were doing this using Plot3D, we would say that we have y as a function of x, y equals f of x, and then we'd have the top function and the lower function, and then we have constant limits for the other variable. And so the setup is going to look like this. I'm going to integrate with respect to y first. So inside my iterated integral, I would have the function that I'm integrating, y divided by x squared plus 1. And then I'm going to integrate this with respect to y first. And the y goes from 0 to square root of x. And then on the outer integral, I would integrate this with respect to x. And then my limits for the x are 0 to 4. Okay. So this is kind of given to you, so it seems like it comes pretty natural. But as we do more of these types of problems, you'll see one of the things to worry about is what to integrate with respect to first, because some might be easier than others. One more thing that I do, I don't know, I wasn't going to do it for this example, but I should just get used to doing it all the time. So integrate with respect to WRT, with respect to, yeah, WRT, with respect to y first. So if I integrate with respect to y first, I should be able to draw lines parallel to the y-axis. I should be able to draw lines parallel to the y-axis where I would enter the region and I would exit the region. So those points where I enter and exit the region should be described by some function y is equal to something with x. Okay. So if I'm integrating with respect to y first, I have my region. I'm going to draw, I should be able to draw anywhere in that region a line parallel to the y-axis where I enter and exit. I enter the same function wherever I go. I exit the same function wherever I go. Okay? Yeah. Yes. Yes. Okay. All right. The setup, to me, is the most important part. The other important part, so when you integrate with respect to whatever first, you should be able to draw a line parallel to that whatever, and then be able to enter and exit the region by the same functions. Okay? And the other important part is that whenever you do a double integral, or triple integral for that matter, you're going to do an iterated integral and work from inside out. The outer limits always have to be constants. Outer limits always has to be constants. Have to be constants. Okay? Cannot stress that enough. And I know in the exams I'm going to see where your outer limit is not a constant, and I'm going to be really sad. I really need to stress this, that the outer limits have to be constants. Tanya. Yeah, it's the last step, and so you need to get a number, and if you have variables in there, you're not going to have a number at the end. Okay? All right, so I suppose we should integrate it now. I think Travis was the one who said, if you're going to integrate this with respect to y2 first, then the x is constant, so we can move that out. Yeah. No, we're always going to be dealing with definite integrals. By the way, well, let's do this. For Travis's suggestion where 1 over x squared plus 1 is a constant, we can move that out of the inside iterated integral and just integrate the y with respect to y. So the antiderivative is y squared over 2. Y squared over 2, we evaluate that from 0 to square root of x. So, and sometimes this might get a little confusing. I sometimes do this in u substitution. When I do u substitution, I remind myself what my variable is. So if you want, you said you just integrated with respect to y, you might want to remind yourself, in case you forget, that these are limits for the y variable. Now, there's only a y variable in here, so I didn't have to worry about it, but just in case. So let's put a square root of y. Square root of y squared is going to be just y, or x, square root of x squared. So it's going to be 1/2 times x, right? And so now that's what you're going to have in here. And let's bring the rest down. I suppose I want to rewrite that a little bit. And this is a simple integral, right? What is it? What do I do? U sub, so u is equal to the denominator. Du is equal to 2x dx. And so that x and a dx would cancel. And I'll have an extra 2 that I need to take out, or 1/2 that pops out. So I'll call that a 1/4 integral. Now, I introduced another variable here, so this is where I really want to be careful. Do you want to change variables, or you want to leave it as x and then return back to it? 0 to 4 we have. So let's keep it as x variables. And if that's always what you do, then you don't need to put x equals 2 here. But again, for myself, we have du over u. What's the integral of that? So ln of u. And then this is where we have the limits, but remember that the limits are x limits. So we'll put everything back in terms of x's. And then we'll put the 4 in and the 0 in. So ln of 4 squared is 16 plus 1 is 17 minus ln of 0, ln of 1 is just 0. So I think this is all you have. Okay. Any questions? Remind yourself how to integrate and how to integrate quickly. All right, let's move on. Looks like we're going to do one example per page here. Let's do number 15. So sometimes you might be able to write your integral in a couple of different ways. Yeah. Yeah, in general, I'm not going to care whether you can integrate or not. I'm assuming you know how to integrate because you passed Calc 2. Whether that's a good assumption or not, it's not going to really matter to me. But setting it up is what I care about. And a lot of times, if I don't care about you, or not that I don't care about you, but if I don't care about you not being able to integrate, then I'm not going to care about me being able to integrate. Which means you're going to see myself, you're going to see me doing a lot of Wolfram alpha to find integrals. I feel confident that I can integrate. And I'll feel confident that you can integrate. Yeah, like I said, I don't care. All right. So, like this one, for example, this would be a good test question, and not that the integral is going to be important, but the setup itself is what's important. So they asked us in the problem to set this up in 2 different ways, and let's see how this would work out. And the D is what you need to figure out. And once you figure out the D, then the next step is to figure out which way should you integrate first, and then set up the integrals. So let's draw this. Again, it's up to you to know these functions. Oh, this is the one Bryce did. I'm going to change the problem. Is it okay? Nah, get rid of it. Let's do number 16. All right, graphing these things is going to be one of your key issues. You have y is equal to x. And the more you're familiar with these graphs, the faster you're going to go. Otherwise, you're going to have to sit there and try to plot points or graph it or whatever. Y is equal to 4 is a horizontal line. And at this point, I still don't know what the region is, because right now it looks like there might be two regions. But the third line is x is equal to 0. So x is equal to 0, it's just the y-axis. So I think we have our region identified. Agree? All right, so this is one of those regions that you can either integrate with respect to x first or with respect to y. And let's set up both integrals because, well, that's what they want us to do. And let's compare the two integrals to see which one might look easier. Okay, you with me on this? Now, let's pick a variable to integrate with respect to first. Like I said, this looks like it could be done either way. And there's some shapes where it would be easier to do, way easier to do one way than the other. So, yeah, Ima? Your answer should be the same, I hope. Yeah. Well, let's see. So, which one do you want to do first? X. She said X. Everybody else said Y. We're going to do both. Let's do with respect to X first. Now, remember the process, right? If I want to integrate with respect to X first, with respect to X first. WRT, with respect to. With respect to X first. I'm going to look at my graph, and hopefully you're able to construct a nice looking graph. And I will draw a line parallel to the x-axis. Okay? And the idea is that regardless of where I draw my line parallel to the x-axis, I should be entering the region by the same function and exiting the region by the same function. So I don't have to draw all those lines. I'm just going to pick one of them. And if I'm integrating with respect to x first, I will need x limits. Okay? And I need to know x equals to what will be my entry point. I start entering when x is equal to 0, right? And then I'll be inside of the function, inside of the function. Now, as I leave the function at x equals what? X equals y. So there are my limits for x. What are my limits for y? 0, 4. Right? So y is going to be my outer limits, and outer limits are what? Always constants. You going to remember that? Outer limits are always constants. All right, I got my integral. So I have inside my integral is y squared e to the xy. And I'm going to integrate with respect to x first. So I'll write dx. And now what are my limits for x again? 0 to y. And then I'll write my second integral, the outside, with respect to y now. and then my outer limits are 0 to 4. Okay? All right, let's put that aside for a second. And let's now do with respect to y first. Okay, with respect to y, again, I should be able to draw lines parallel to the y-axis, and hopefully the functions remain the same for whichever line I draw. So let's just draw this line going through the region, and as I go from negative to positive, I will enter the region at the function y is equal to what? Y is equal to x. I'll be inside of the region, and then I will get out of the region at y is equal to what? Constant 4, right? Limits for x, 0 to 4, constants. How'd you get 4? That's where it ends, right? Okay. The inner integral. So y squared e to the xy with respect to y is going to go from x to 4. With respect to x, going from 0 to 4. Okay? So these two are equal. What do you notice? In when I talked about this, when we were just talking about rectangular regions, I had constant limits for both. And I switched the order. Fubini's theorem says I can switch the order and everything would be fine. Imagine if you took an integral that did not have constant limits and you switched the order just by switching the order. So that you go 0 to y, 0 to 4, y squared e to the xy dy dx. Is this valid? No. You cannot just switch the order to get the same integral. Okay? It violates that rule where the outer limits have to be constant. All right, now, Hema was asking about, well, you can write it either way. What would be easier to do? If you look at this integral, let's look at this one first. According to this iterated integral, I have to integrate this with respect to y. I have y squared e to the xy. How would you do this integral? Probably by parts. I think it's manageable. Twice by parts. I think it's manageable. But let's look at the second integral. Y squared e to the xy with respect to x. So y is a constant. That can go out, and you just take the integral with respect to x. You can even pull out e to the y, and then you just have e to the x. Right? Oh, it's plus. Yeah. Good catch. I believed them. In any case, it'll be easier. This will be easier. Okay. So let's pretend that we did the integral and we're all happy and let's move on. I'm not going to do it because I know you guys can integrate and I have faith in you that you pass Calc 2 and you're all integral experts. Let's do another example. All right, we have integral of y squared, that's easy, over the region D, where D is a triangle with vertices at 0, 1, 1, 2, 4, 1. All right, it looks like we need to draw this triangle region thing that they have. 0, 1, that's in the y-axis. 0, 1. 1, 2, 1, and then 2. 4, 1. 1, 2, 3, 4, and then 1. All right, got ourselves a domain or a region. So, what do we want to integrate with respect to first? Why? Why? Because what? It's flat on the bottom. Okay. So let's integrate with respect to y first. I think I have an issue here. What's my issue? I have two different functions to have to deal with. Do you see that? If I'm over here going from 0 to 1, and I'm going to set this up. We can set this up, but you'll see some complications happening if we integrate with respect to y first. So with respect to y, I would draw lines parallel to the y-axis, and I would draw a bunch of sample lines all throughout the region. And when I do these two lines in particular, I see that when I go into the function, I'm going to go into the function at y equals to what? That's the line y is equal to 1, right? So I'm going to go y equals to 1. And then when I get out of that function, I need to find the equation of this line. What's the equation of that line? I think it has a y-intercept of 1 and then a slope of 1. Yeah? Say it again? Yeah, that's what we have to do. Okay? So, did you hear? We have to split it up into two integrals. Okay, so that's what we're going to do. We're going to set it up. But we'll see that if we do it the other way, with respect to x first, we're only going to have one integral. And I prefer to do that. But let's do this one where we have to split it up into two. So I think the outer function is going to be x plus 1, and my x limits go from 0. But now if I go past 1, my top function is going to change. So I can only go up to 1, and then I need to change functions. So I need to add on another integral with different y limits and x limits. Okay, so after I go past x is equal to 1, my cuts now are going to go from 0 or from 1, y is equal to 1, and then now I need to get out of this other function. This one it's still a line, but I need to figure out what the slope is and the y-intercept and all that. So can somebody help me with that? The slope is negative a half. Oh, negative 1/3. So the slope is negative 1/3. Can you imagine this hitting the x-axis or the y-axis? Has to be bigger than 1. 2 and 1/3. 2 and 1/3. 2, 6, 7, 7/3. Just to make it into a fraction. Y equals mx plus b, and then you put like 1, 2 in there or something like that, and then you find your b. So, and then my x is going to go from where to where? From 1 to 4. So if you paste these two integrals together, you would find the whole area. So you'll have a double integral y squared dy going from 0 to x plus 1, and then dx going from 0 to 1. And then you'll have another integral y squared dy. This one goes from 0 to negative 1/3 x plus 7/3. And your x goes from 1 to 4. Okay, so that's manageable. It's doable. But let's take a look at the alternative. What if instead somebody yelled out with respect to x first? Then we would draw a line parallel to the x-axis. And then regardless of where we drew this line, we would always enter the same function and exit the same function. So with respect to x first, we will need an x function or a couple of x functions, or the lower and the upper. So I would be running along here parallel to the x-axis, and I would hit my region at this graph, but I want this graph in terms of x or in terms of y. So y minus 1. And then I would be inside of the region, and then I would be exiting this other line function. And again, we want that in terms of x. So be 3y is equal to minus x plus 7. So x is equal to 7 minus 3y, something like that. Okay. What are my other limits, y limits? Beware. Y limits. So y is from 1 to 2. So y is equal to 1 here, y is equal to 2, and that's where you end. Okay, looks like we only have one integral here. First, with respect to x, and we have y minus 1 in the bottom, 7 minus 3y on top. And then with respect to y, constant limits going from 1 to 2. I'd rather integrate one integral. Okay? So in the book, they refer to these as type 1 or type 2 regions. I don't really care for those names. Type 1 regions or type 2 regions are regions where if you integrate with respect to one variable, then you have one integral. If you integrate with respect to the other variable, you might have two or more integrals to do. So this is one of those types regions that would only make sense. Well, not only make sense, but would be easier to compute because you only have one integral if you do it with respect to x first. Okay, questions? All right. Let's do another one. Much like area under the curve, the single integral is like the area under the curve. A double integral can be seen as a volume under a surface. The area under the curve, your limits are just from A to B, which is just an interval in one dimension. Your x goes from A to B, whatever they are. But when we're talking about double integrals, your base is a two-dimensional region, and then you get height. So area under the surface of z is equal to 1 plus x squared times y squared. And above the region, so this is the region that sits in your two-dimensional plane. The region is x equals y squared, and x is equal to 4. Again, it would be good if you know what this graph looks like without having to think about it too much. I have an x and a y is squared, so this is some sort of a parabola. Since the y is squared, it's probably going sideways. And so go through a thought process like that when you're trying to describe the two-dimensional graph of something. All right, so the first thing we want to do is to handle this region. This is a sideways parabola. X equals 4 is a vertical line. So I think the region is pretty straightforward. So we can call this D or R. So the volume should equal to double integral over R of 1 plus x squared y squared dA. So dA is what we generally use when we're not ready to figure out what we're going to integrate with respect to first. So just to set up the problem, I say dA because I haven't decided if I'm going to do dx dy or dy dx. Now let's decide. Given the shape of the graph, what do you think we should do? With respect to x first or y first? Y? So if you do with respect to y first, you would draw a line parallel to the y-axis, and you would look at the places where you would enter and exit the region. Not only that, you would also need to express where you enter and exit the region with y's. So if you do this with respect to y first, what are your y limits? I enter the region, y is equal to what? Negative square root of x. I'm not liking this already. And you exit the region. Doable, but I probably wouldn't want to do it this way. Let's finish it. What's x? 0 to 4. Okay? All right. Let's not put the integral yet. Let's take a look at the other one. If I draw a line parallel to the x-axis, regardless of where I go in my x, I would be entering and exiting the same functions, right? So what is my lower limit for the x? Where do I enter the region in x? Y squared. And then I exit the region, x is equal to 4. Okay? And then my y limits is what? Don't say square root of x, positive square root of x, negative square root of x, because that's not the answer. What should it be? 0, 2? I probably, yeah, so I want to go all the way down here and all the way up there. Now, there's stuff with symmetry where you could possibly go from 0 to 2 and multiply it by 2 if you're confident about the symmetry of this graph, which I think in this graph it is kind of symmetric, but I often refrain from doing much symmetry stuff. All right. So I don't know which is better. I think just to avoid dealing with square roots, because when you do this, you might have like a cube root of something, or y to the 3/2 or something. I don't know. I would probably just stick with this. So set up this integral. The inner integral, or the integrand itself, is 1 plus x squared y squared. Now I'm going to integrate with respect to x first. So dx, my x limits go from y squared is my lower limit, my upper limit is 4. And then dy, my outer limits are constants, minus 2 to positive 2. That looks pretty manageable. I'm dealing with polynomials, power functions, no square roots. Okay. So in your homework, you'll have a lot of integrals, and you actually have to compute them. Let me give you a hint. Integrate, open parentheses. Integrate again, open parentheses. 1 plus x squared times y squared. So inside of the first integral, I'm going to integrate my x, and my lower limit is y squared dot dot 4, close parentheses. That's my inner integral. My outer integral is going to be with respect to y, and the limits go from minus 2 dot dot positive 2, close the integral interval. Okay. Questions? So this is your volume. And you can use CalcPlot 3D to get this. Well, let's try it. I don't like the box. Okay, we have the region. So what kind of function are we dealing with here? Is it y equals f of x or x equals f of y? What? X equals f of y, right? Yes. Okay. So x equals f of y. And then they want to figure out what the right function is. The function on the right is what? Y equals. It's like the top limit of the inside integral. Y equals 4. What's the bottom limit? Is it y squared? And our limits? Minus 2 to 2. So the numbers and the expressions that you put in these boxes are actually the limits of your integration. I don't know if you guys are noticing that, but that's what's happening. I need to make this bigger so that I can see what's happening. The y max. All right. Uh-oh, what happened? My y got cut off. Really? So this should be 4. I got turned around here. All right, that's better. So you see the two-dimensional graph matches our two-dimensional graph. And then now let's put the actual function here, which is 1 plus x squared times y squared. Wow, that looks kind of cool. If we ask them to show Riemann prisms and then make this, you know, the more partitions you have, the finer you get. Their approximation's about 79-ish. What was the answer that we got? 86. Huh, that's still way off. Any case. Anyways, you have that picture. You can get those pictures and see how the graph might look like. So there was some symmetry in there somewhere, if we cared to really dive into it. Okay, any questions? All right. Now let's do another problem. Let's just do a whole bunch of examples. 30 or 31? 31. Bounded by a cylinder, x squared plus y squared is equal to 1. So that's a circular cylinder going up along the z. The planes, y is equal to z, x is equal to 0, and z is equal to 0 in the first octant. So the first octant, everything is positive. So x is 0, y is 0, and z is 0 would be boundaries for this. Let's see how this thing looks like. I feel like just going to CalcPlot 3D. Now let's see if we can figure this out. So I'll start off with a cylinder. The plane x is equal to 0 and z is equal to 0. Z is equal to 0 is on the xy plane. So that gets cut off right here. X is equal to 0 is on the yz plane. So yz plane, that gets cut off here. And y is equal to z. So y is equal to z is a line on the yz plane that sweeps over and does that. Wow. Can you picture it? It's in the first octant, so we're looking at just the positive part. Whew. Somebody probably has a better drawing than me. So it's in the first octant, so what you could do is maybe you can imagine a quarter of a cylinder and then a plane cutting it this way. So cutting a wedge out. So what you would have left would be like a wedge part. Let's look at it from the top. Because I'm probably going to be interested in looking at this in terms of x and y to figure out my domain. What's my domain going to be? It's hard to view, huh? Yeah. So let's start with the region. Shaheen said it's like a circle, almost a circle, except it's in the first octant, so things got cut out. What is the region? If you were to look at this from the top, what are you seeing? I would probably be seeing a quarter of the circle because in the first octant, everything else gets cut off, right? So that's my top view. And not only that, but this is going to be my region. Is that okay? So when I work with this, this is going to determine my limits for x and y. Now, Shaheen also said a plane. This is a plane right here. This is a plane that's a little bit slanted, right? A little bit slanted, cutting that quarter of a cylinder. So this will be your top. And your bottom would just be in the first octant, so the bottom is going to be 0. So it looks like your top function here is going to be z equals what? That's the plane right here. Z is equal to y. There's no x's. For some reason, this didn't depend on x, but that's okay. So this is going to be the integrand. So the volume is going to be a double integral over d of y dA. So now we just have to figure out what d is. What do you want to integrate with respect to first? Doesn't matter. Well, it might matter because the y is there. So it might come in handy later. But let's integrate with respect to x first. Y first. Let's do with respect to y first. I don't know. Let's y or x first. Let's do with respect to x first. All right. I draw a line parallel to the x-axis. Draw a line parallel to the x-axis. I would enter my region when x is equal to what? And I would exit my region. Ooh, we didn't really talk about this function much. What is this function? Yeah, that stuff. It's a circle, right? And so you solve for x probably. And when you solve, you get plus and minus, but this is positive. So just the positive part. Yeah. You could if we were in tomorrow's lecture. And then how about your y limits? Always constants, 0 to 1. Now you have your integral. So with respect to x first, going from 0 to 1 minus y squared in the square root, and then 0 to 1 with respect to y. Yeah, so this probably would be easier because you'd integrate this, you'll have a y times 1 minus y squared, and then you do a u substitution, it'll work out. Or, like Matthew said, tomorrow this will be a piece of cake. I don't think you have to, because after you put in these limits, this y is sitting out here and just a u sub. I mean, you can still use a trig sub if you want. But we want to avoid those things. We want to simplify our lives as much as possible. All right, let's do one more. Back in Calc 2, there's a few functions where we said, oh, we just cannot integrate that. Here's one of them. E to the x squared. What? It's just Earth. It's just Earth. Earth. It's just the earth. Earth. All right, no, we don't want to do that. We can't integrate this. Or we can't integrate it if we're trying to integrate with respect to x first. So what if we change the order of integration? How do you change the order? Do you just switch it? Got to draw the region, right? So the inner integral is x. So my x limits, lower limit at 3y and upper limit is at 3. And then my y goes from 0 to 1. Okay, so let's draw that. X is equal to 3. I think I do better if I write this in terms of y. So I see a slope of 1/3, so not very steep. And then my x is equal to 3. And my y goes from 0 to 1. I'm assuming this is 1. So that's my region, it looks like. Now I couldn't do it integrating with respect to x first, so I'm going to integrate with respect to y first. Draw a line parallel to the y-axis. Y goes from where to where? 0 to that line. And x goes from where to where? Now, for some reason, this is supposed to be easier to integrate. What's the integral of this thing with respect to y? All right. Y e to the x squared from 0 to 1/3 x. And you'll see after you put that in that it'll end up just being a u substitution. So it's actually doable now that we switch the order. So sometimes you might need to look at an integral, start off saying, oh, I can't integrate that. But if I switch the order, maybe it might come out easier. And that's what happens here. Okay, so I'm going to finish this in the notes and then post it if you want to see the solution to the rest of this stuff. And I'll add some more pictures with a couple of examples that we did. But tomorrow, we're going to integrate those that go around in circles using polar coordinates. Okay, see you guys.